Howdy, folks. Well, we're here for the second installment of our solubility equilibria discussion. Now, today what we're going to look at is the very last topic in chapter 18, and this is on complex ion formation. And this is kind of a special topic because these are equilibria that definitely favor the product side of the equilibrium. We've been looking at a lot of very weak equilibria that definitely don't favor the product side. We looked at weak acids, we looked at weak bases, we looked at marginally soluble solids that barely creep out into the solution. But it turns out these complexes that we're about to look at are extremely stable, and when they get formed, the equilibrium definitely favors the product. This throws a little bit of a twist into the mathematics that we have to do. But first, a little discussion about how these complexes actually form. Now, back in Chem 130, we may have or may not have mentioned something called a coordinate covalent bond. Now, this is a kind of a bond where one of the two species that's bonding together donates both of the electrons to form the covalent bond between the two of them. You remember the rule of 8 and us drawing Lewis structures, and there was always this sharing of electrons between atoms. Well, when one of them donates both the electrons, that's called a coordinate covalent bond. For example, when an ammonia molecule, which has a lone pair on it, this is the Lewis structure for ammonia, NH3, when it reacts with a hydrogen ion and forms a bond here, you can see that both of the electrons are being donated by the ammonia, by the nitrogen, and forms an ammonium ion, where this new covalent bond, again, is a coordinate covalent bond because the nitrogen donated both of those electrons to form that bond. These types of coordinate covalent bond formations actually fall under the umbrella of Lewis acid-base reactions. We touched on this briefly at the end of our chapter on acids and bases. And if you recall, a Lewis acid and base pair is an exchange with an electron pair. The base under the Lewis definition is the electron pair donor, where the acid is the electron pair acceptor. Well, if you look at this reaction between the ammonia and the hydrogen ion, clearly the ammonia is the Lewis base, it's the electron pair donor. And the hydrogen ion is the electron pair acceptor, the Lewis acid. The hydrogen ion pretty much fits the definition of an acid, regardless of what concept you're actually looking at. So sure enough, this is a Lewis acid-base reaction whenever a coordinate covalent bond is formed between two species. Well, it turns out that the metals, particularly the transition metals, have a tendency to be great Lewis acids. They're great electron pair acceptors. Let me make a little bit of room here and we'll explain why. Okay, well, back in the day when we talked about electron configurations, that was that 1s2, 2s2, 2p6 business. The copper ion in its ground state would have been an argon core with a 4s1 3d10 arrangement. But being a +2 ion or even a +1 ion, it's going to lose that valence electron in one of these 3d electrons. But remember, there's still out in this valence shell a 4p subshell that isn't being used. It's unoccupied. Well, it turns out that copper then can provide some uninhabited orbitals to accept a pair of electrons to form a sort of coordinate covalent bond with something. And as a matter of fact, copper +2 will form sort of a tetrahedral shape of vacant orbitals that things can attach to. Well, if something were to come along that wants to donate a pair of electrons, let's use our example of an ammonia molecule. It can drop that lone pair of electrons right into that vacant orbital and suddenly form sort of a coordinate covalent bond with the copper, now sharing electrons with the copper. Well, it turns out copper actually has 4 sites where this can happen. And so an ammonia can actually lay a lone pair in there in each one of those 4 lobes that sticks out from the copper. Well, this forms kind of an interesting complex because, let me erase this and draw it a little bit better. What we end up then with is a copper +2 in the center and an NH3 at the points of a tetrahedron here. Let me just put an NH3 at the end of each of these. That probably look a little better. Where the lone pair from the nitrogen is actually taking up occupancy in a vacant orbital that belongs to the copper. It turns out that these complexes, and note that the copper still maintains that +2 charge because the ammonia molecules are actually neutral. So this is a huge complex cation with a net +2 charge on it. So it could actually interact with an anion. For instance, this could couple up with, say, a couple of chloride ions to form what's called a coordinate complex. All right, a complex is something that contains a complex cation or a complex anion. And the molecules that do the donating of the electrons to the copper or to whatever transition metal we might use, these are referred to as ligands, L-I-G-A-N-D-S. I mentioned this on the audio lecture that's online. So again, take a look at that one, sort of use this as a supplement. All right, so complex ions can be formed then with transition metals and Lewis bases that we'll refer to as ligands that can donate a pair of electrons into a vacant orbital and form these complexes. Now, like I said before, these aren't weak equilibria. When this molecule forms, the equilibria definitely favors the product side. As a matter of fact, let me write out the reaction and we'll look at the equilibrium expression for it. All right, well, the reaction of the copper +2 ion with 4 ammonia molecules, NH3 aqueous, to form this complex cation, Cu NH3 4 +2. Now this ion is not a solid, it's actually an aqueous ion. So consequently, when we write the equilibrium expression for this, unlike the KSPs that we just looked at in the last module, there aren't any solids here that are going to drop out. Everybody plays, everybody stays. So this is why I always thought that complex ion formation should have a separate chapter, because suddenly the denominator is back in our equilibrium expression. It would be the concentration of the complex, NH3 4 +2, over the concentration of our reactants, copper +2, and ammonia raised to the 4th power. Again, oh, I'm sorry, let me put that +2 inside the brackets. That looks like a power. So it's not raised to any power because there's no coefficient there. But the ammonias are raised to the 4th power. Now it turns out that these equilibrium constants are called K sub F to stand for formation constants. And as I mentioned earlier, these formation constants are usually very large. The equilibrium, the stability of these complexes forces the equilibrium to go very far to the right, meaning the top of this fraction is very big, the bottom is very small. So these are generally very, very, very large numbers. As a matter of fact, let me quickly just go look up the K sub F for this particular complex of the copper. Hold on just a second. Oh, the formation constant for the copper and 4 ammonias, 4.8. The K sub F for this one, 4.8 times 10 to the positive 12. Now, again, we haven't seen equilibrium constants to positive powers this big, so this is a pretty good indicator that this equilibrium definitely goes pretty far to the right. Now, that poses a big problem because the mathematics can get a little bit complicated since any minus x's on this side or minus 4x's here are not going to be able to be ignored. They're going to be very large because a lot of it's going to disappear from this side of the equilibrium. And it can make huge polynomials to solve. All right, as a matter of fact, let's set up a problem and put some molarities to this actual complex. Okay, well, looking at this equilibrium, this formation of the copper complex with the ammonia, and again, it has a big formation constant, 4.8, 10 to the positive 12. obviously it's going to go very far to the right. And suppose we started off with a 0.015 molar concentration of copper and a 0.100 molar concentration of ammonia. So in this case, the copper would be the limiting reagent. There's plenty of ammonia there. There's going to be some left over if we were to gobble up all of that copper and go 100% across the arrow. Well, ultimately what their question is going to be is, in the presence of this ammonia, how much of that free copper is actually still going to be left in the solution? Because most of it's going to be gobbled up. So generally what their question is, well, in the presence of that ammonia, is there going to be likely to be any of that copper ion left out on the dance floor? Well, it's not going to be much, but that's what we want to find out. All right, well, in the approach of this equilibrium, here's the problem. If we were to do this like our normal ice table, we would end up subtracting an X amount from the 0.015, say an X number of coppers gets across the arrow, and a 4X number of ammonias would go across the arrow. Well, this is the issue, because if that were to produce then an X amount of the complex, if we plugged all of this into our equilibrium expression, 0.015 minus X for the copper, 0.1 minus 4X for the ammonia, and X for the complex, here's the problem we would have had. We would have set the Kf equal to our product over our reactants. So this would have been X over 0.015 minus X and 0.1 minus 4X to the 4th power. Well, that's going to be a 5th degree polynomial down here in the denominator. And I don't know about you, but I've left doing 5x5 matrices way in my past. So it turns out that we need to take another approach to this unless we want to fight that almost insurmountable polynomial right there. Okay, so here's my thinking on it. Let me make a little bit of room here, and I'll explain. And again, we're just going to do this so we can simplify the math and not have to solve these huge polynomials. If we were to just change the perspective of this equilibrium, meaning when you're looking at equilibrium, it's almost like being on two sides of a street. You know, if you're looking at here's your reactants, here's your products. All right, so in a very weak equilibria, you don't get very far out into the street before the reaction reaches equilibrium, meaning you don't get very much product. You're not getting close to that curve. And the minus X amount that you lost from your reactant is always very small. Consequently, we could ignore it, and the mathematics fell apart really nice. So weak equilibria are handy because you can ignore all the added and subtracted X's, and the math just crumbles into something simple. But our problem is that this is not a weak equilibrium. This is a very strong equilibrium that's going to go almost all the way to the product side. Let me just say that it wants to go right there. That's its equilibrium point. And now the minus X that we lost from the reactants are huge and can't be ignored, which leads us to some ugly polynomials to solve. All right, so here's the approach. What if we just changed the game? What if we stood, instead of on the reactant side, what if we stood on the product side and let it approach the equilibrium from this direction? Meaning, let's push it to the other curve and flip it over and make this the reactant side and this the product side. If that's the case now, approaching the equilibrium from the other direction would make it a very weak equilibrium. As a matter of fact, the equilibrium constant from this side of the street would be the inverse of that number, which would make it very small, meaning that the X amount that we would lose from our reactants, if we looked at it from this standpoint, would be a very small number and easy to ignore. All right, so let's approach it this way. As a matter of fact, to do that, we need to get to the other curve first, meaning let's push it all the way to the curve, and then let's see how much of it tries to creep its way back out to reach that equilibrium point that it's trying to seek. All right, let me get a little room here. Let's treat this first as a limiting reagent problem. Let's make as much product as we can and exhaust whatever we've got on reactant side. that will essentially push us to the other curve. All right, well, copper is the limiting reagent, so let's assume that it goes to 0, meaning it lost all 0.015. Well, this is going to lose 4 times 0.015, or 0.06, so essentially that's going to leave 0.04 molar of the ammonia still remains. We had some excess there because, again, the copper was our limiting reagent. Well, in the losing of that X amount, that 0.015 from the copper, we would have created 0.015 of the complex. So at equilibrium, or not at equilibrium, but at the other curve, if we just artificially push the pendulum all the way to the right, we could conceivably make maximum 0.015 molar of the complex, leaving nothing of the copper, but leaving 0.04 molar of the ammonia still remaining out on the dance floor. All right, well now what we need to do is, now that we're standing at the other curve, let's cross the street and look at the reaction from that direction. I'm going to flip it over. These, by the way, are now going to be my initial amounts from the other curve, looking back at the equilibrium being established, going back toward the left. All right, so let me flip it over. Okay, so I flipped the reaction over. Now we're standing on the other curve. We're looking at the complex being formed, or being decomposed into copper and the 4 ammonias. And our starting amounts, once we pushed it all the way to the completion side of the street, we had 0.015 molar, theoretically, of the complex formed, leaving no copper and leaving 0.04 of the ammonia. From this direction, the equilibrium constant is 1 over the Kf, which is 1 over 4.810 to the positive 12th, which makes this Kd a very small number. We'll calculate it here in a minute. But looking at it from this perspective now, any subtracted X, meaning the complex sort of creeping back toward its equilibrium to leave a little bit of copper out there free in the solution. And again, this is what we're looking for. We want to know how much of that copper would actually be left. Well, at equilibrium then, this is going to be 0.015 minus X. This is going to gain an X amount. And this is going to gain 4X. 0.04 plus 4X. All right, now here's what's handy about looking at it from this side of the street. Our equilibrium constant's very, very small. So that means we're not going to get a lot of product here. The X's are going to be really small. That means we could likely ignore this X. So this is going to be approximately 0.015 molar, not 0.015 minus X. As a matter of fact, the X's are so small that even 4 of them is not going to make a dent in that 0.040. So this is going to be approximately 0.040. All right, well, let me make a little bit of room here, and we'll plug these variables into our equilibrium expression for the dissociation of this complex. Okay, so our dissociation of this complex then, the equilibrium expression for it would be the products over the reactant. Again, the copper and the ammonia now are the products in this weak equilibrium. The ammonia again raised to the 4th power. Remember that the equilibrium constant for this is the Kd. It's 1 over the Kf. And we figured out that at equilibrium, the concentration of the complex would have been 0.015 minus X, but we ignored the subtracted X. The amount of copper that was left would be the X amount in this expression, and the amount of ammonia was 0.040 plus 4X, but again, we ignored those 4X's because, again, the X's are very small. All right, well, let's plug in some numbers here. All right, well, 1 over 4.8 times 10 to the positive 12 is our Kd. Now, we could go ahead and calculate that. I think it comes out 2.08, 10 to the minus 13th, but we'll just leave it as an inverse of the Kf. That's going to be equal to X, our copper concentration. Remember, the ammonia was 0.04 plus 4X, but we're going to ignore the plus 4X, to the 4th power. The complex was 0.015, again minus X, but we're going to ignore it. So essentially then, notice when we solve this, we don't even have to do a square root to find out the value of x. And it turns out x is 1.2 times 10 to the minus ninth molarity in copper. That's how much copper would actually be left in the solution. Now think about this. Where did the copper start? It started at 0.015 molar. That's 1.5 10 to the minus 2. It dropped all the way to 1.2 10 to the minus ninth in the presence of this ammonia. So essentially the ammonia just gobbled up all the copper. And in order for us to figure out, well, how much of that copper, that little minuscule amount, is still left out there floating around, we had to push this reaction to the other curve, flip it over and look at it as a dissociation, just in order to be able to ignore all those added and subtracted x's. The only reason we did it this way was to make the math a little simpler. All right, well, I'd like to do another example. Let me clear this off and we'll do another. Okay, here's a good one for us. It turns out that the cyanide anion, its Lewis structure, by the way, looks like this. It's a carbon triple bonded to a nitrogen, lone pair sticking out of each end. The reason it can kill you is because it complexes very nicely with the iron that's in the hemoglobin in your blood. And once it's complexed with the cyanide, your blood's not going to carry any oxygen anymore. So this is why cyanide is a little bit dangerous to us. And it forms a very, very stable complex with iron plus 3. As a matter of fact, 6 of those cyanides will arrange themselves in an octahedron around that iron plus 3, occupying 6 orbitals, laying a lone pair from the nitrogen in each of those orbitals. The formation constant for this is 9.1 10 to the positive 41st power. So this is a very, very stable complex. If we were to put iron plus 3 in the presence of any cyanide solution, virtually all of the iron is going to get gobbled up. There will be just a minuscule amount of the iron plus 3 still left in solution. All right, well, let's throw some numbers on here and see what terrible mess we can make. All right, well, suppose we make a solution that's 0.1 molar in something like iron plus 3 nitrate, FeNO33. Very soluble. The iron dissolves very readily that way. But then we dump in some sodium cyanide. Again, the sodium, just the spectator ion. It's the cyanide we're really interested in. And we put in enough to make this like 1 molar. Well, that cyanide is definitely going to be on that iron and form this complex. And consequently, the equilibrium is going to go as far to the right as it almost possibly can, almost to the other curve, not quite all the way there. Our question is, after it gobbles up that iron, how much of it is left? That's their question. All right, well, again, the easiest way to do this is to treat it like a limiting reagent problem. Let's just let it have its way and go all the way to the other curve, then we'll flip it over, look at it as a very weak dissociation of this complex. All right, well, again, limiting reagent-wise, it looks like the iron plus 3 is going to run out first. So let's just go ahead, and they'll do that each time on these problems. They'll make it in such a way that your metal ion is going to be your limiting reagent. So all of this 0.1 is going to disappear and leave us with nothing. Here we're going to lose 6 times the 0.1. So we're going to lose 0.6 of this, leaving 0.4 molar of the cyanide still remaining in solution. And we're going to make in the process 0.1 molar of the complex. We made as much of it as we possibly could before this ran out. So we pushed the reaction all the way to the curb on the other side of the street. Our question is then, how much of this would try to creep its way back out into the street as a KD, a dissociation? So to do that, it's easier if we just rewrite the equation. Let me go ahead and flip it around and rewrite it. And we'll put these then as our initial amounts from the other side of the street. Okay, so I've rewritten the equation, flipped it over, and now we're looking at the complex and how much of it would actually dissociate, kind of bounce back. And remember that the Kd, the dissociation constant for this, is 1 over the Kf, which was 9.1 10 to the positive 41st power, which makes this Kd mighty small. All right, so we just treat this like a regular weak equilibrium now. We lose an X amount on this side, we gain an X amount of iron, and we gain a 6X amount of cyanide. So this would, at equilibrium, be 0.1 minus X. This would be X. This would be the 0.4 that remained, plus the 6X that it would get as this dissociated. But again, it's not going to dissociate. The number is going to be so small, the X's are, that subtracting it from 0.1 won't make any difference. So we're going to ignore this one. And as a matter of fact, we're going to ignore all 6 of these. All right, well, let me make a little bit of room and we'll just do the number crunching. Okay, well, we plug in our variables and we find products over reactants. Here was the copper, the iron, plus 3. Here was the cyanide, the 6 of them. And this was the complex. Well, if that's the case, then the dissociation constant, 1 over 9.1, 10 to the positive 41st, would equal X, the iron concentration. That's what we're looking for. That's the answer we want. Here's the cyanide that was remaining, 0.4, which would have been plus 6X here. But again, we ignored that 6X. This would have been 0.1 minus X, but from this side of the street, the X is small. Ignore it. So now you can see this is actually very easy to solve. Devin? No, actually, Ethan, you back there in the corner? Well, somebody calculate this. Hold on just a second. I got to go find my calculator. All right, well, I found that X was equal to 2.7 10 to the minus 41st power molarity in iron plus 3. That's virtually non-existent in the solution. So the cyanide pretty much did gobble up all of the iron and only left this little minuscule amount out there in the solution. Okay, so you can understand then that in the approach to these problems, they're always going to give you the concentration of some metal ion. They're going to attack it with a ligand, a Lewis base, and gobble up as much of it as they can. The point they're trying to make here is that even though a strong equilibrium at first might look like the mathematics is going to get out of control, if you just change your perspective, push it across the street, flip it over, and look at it as a weak equilibrium, you find the mathematics just crumbles. All right, well, we got one last topic for you in chapter 18, so let me clear the board and we'll get to it. Okay, this last problem I have for you kind of combines this concept of KSP, these marginally soluble compounds, and the formation of complex cations and anions, these formation problems. Well, a particular compound of copper, for instance, copper hydroxide, not very soluble in water. It's got a KSP 2.6 10 to the minus 19th power. So it's pretty easy to precipitate copper out of a solution by putting just a little bit of hydroxide in there. As a matter of fact, let's look at a problem. Will a 0.015 molar copper solution, copper plus 2 solution, and again, this would have to be in there with like nitrates or some anion, but if it was 0.015 molar in copper, would copper hydroxide precipitate if the pH was up around 8, meaning it was slightly basic? Well, this is a QSP problem. So let's look at it. The QSP would be whatever the current concentration of the copper is times whatever the current concentration of the hydroxide is squared. All right, well, we've established we've got a solution that's 0.015 molar, so this would be 0.015. The hydroxide concentration at pH 8, now this is really going to pull on something from a few weeks ago, that would mean that the pOH was 6. So the hydroxide concentration with a pOH of 6 is 1 times 10 to the minus 6. All right, well, let's put in 1 times 10 to the minus 6 for the hydroxide. That would be squared, right? Well, our QSP turns out to be, this would be 1 times 10 to the minus 12th, so this would end up being 1.5 times 10 to the minus 14th. Now notice that that's significantly bigger than the KSP. So we've definitely overpacked the dance floor, and yes, this is going to precipitate. But here's my question. Would that same precipitation occur if we had thrown some ammonia in this solution? Now the ammonia would actually complex with the copper ion and sweep the copper ion off the dance floor. Well, if it removed enough of the copper from this solution and reduced this enough, this precipitation may not occur if this number, this concentration of the copper, got small enough. All right, well, let me erase this. I just want to remind you of the problem we just did a little bit ago. As a matter of fact, we did a copper problem with ammonia and said, what if the copper was 0.015 molar and we put the ammonia in at 0.1 molar? Well, do you remember what happened? This fell. We did the whole problem. We went all the way to the other curve. We flipped it over. We did the whole equilibrium shot, the dissociation. This fell to 1.2 10 to the minus 9th in the presence of that ammonia. All right, so I guess my question is, when we put the copper in there with just the hydroxide, yes, it precipitated. The QSP was bigger than the KSP. But what if there had also been a little bit of ammonia in there to remove this copper, reduce it enough so that the copper and the hydroxide would not precipitate? And that's exactly what happened. What happens if we put in 1.2 times 10 to the minus 9th here, which would be the result if this was in the presence of some ammonia? Well, now you can see that the product of these two numbers is going to be, what is that, 1.2 times 10 to the minus 21st, which is less than the KSP of 2.6 times 10 to the minus 19th. So suddenly a little bit of ammonia in there to remove that copper and reduce its concentration can essentially avert the precipitation of the copper hydroxide. All right, so you can see that there's ways to entangle these two problems together. Fortunately, Tro took a nice, easy approach and gave you a couple simple examples like you saw earlier in this module. And so again, take a look at the homework problems that pertain to this particular topic. And well, that pretty much wraps it up for Chapter 18. Okay, well, if you've listened to the narrated PowerPoint lectures that I've got on the website, you'll notice that this section, Module 2 in the Solubility Equilibria, talks a little bit about the qualitative analysis labs that we've been doing and how we group metal cations into 5 analytical groups. We looked at group 1, which was silver and lead and mercury, and it turns out that these precipitate very nicely as chlorides, meaning that the KSPs are very small. So the point I was trying to make in doing that on the PowerPoint presentation was to show you that this whole concept of KSPs and solubilities is what allows us to do those qualitative analysis labs, to selectively reach into a group of metal cations and sort of cut one out of the herd so that we can get it by itself in order to analyze for it. Well, what we need to do is look at comparisons of KSPs and think, well, what anion could I send in there that would specifically target one particular cation? Meaning when it's on the floor with that cation, the KSP doesn't allow that, and it would precipitate out but leave everybody else out there. So you can understand that our qualitative analysis labs basically incorporated this. We looked for specific anions that we could send in to precipitate out one cation and leave the others in the filtrate. And in the next level, we would send in another cation, or another anion, I'm sorry, and selectively precipitate another cation out of the group. All right, so please watch that audio presentation that's online. I think it's a handy explanation for the qualitative analysis labs. If you have any questions on this complex ion formation, I know that these problems are a little bit different than the KSPs, considering that you have to look at the equilibrium first as a limiting reagent and then flip it over. Makes them a little bit more complex. The problem that is in your textbook, hold on just one second. Numbers 109 and numbers 112 are the two that I assigned out of chapter 18. And I think you'll find that the first one that I mentioned, what was that, 109? Number 109 pretty much follows exactly the scheme that you just saw here. There's a table of the formation constants for the complexes that you'll find in your textbook. But again, they leave it up to you to find the dissociation constant once you flip it over. Just take the inverse of the formation constant. All right, so if you have any problems with this, please just send me a text or send me an email. And by the way, I'm going to try to set up a Zoom meeting so that we could do something live and answer questions. And so for those of you who may already have Zoom on your phone or on your laptop, if you'd let me know, just send me an email and let me know that you're up to speed on that. And if not, if you could download Zoom, and if that turns out to be an issue that people don't want to do that or haven't got access to the app, then we'll scratch the idea. But I'd like to give this a shot. So anyway, let me know your thoughts on it. Send me an email. Let me know what you think. And next Monday, I'll start the first lecture on thermodynamics, which is chapter 19. We'll probably do 2 or 3 lectures on that. So again, just keep your eye on your email. I'm sorry that first day's lecture came in so late. I wanted to get this one ready a little bit early so I can get it to you tomorrow on Wednesday. And in addition, I'll send you the link to the KSP lab. Now, I think you still have a lab quiz that you need to submit to me, so don't forget that. So when you turn in your Wednesday lab, make sure that you also scan or take a picture of your quiz. All right, well, I do have one quick story for you, though, before we quit. Is back when I was working for the State Water Survey, and I think I told you folks this story once before, we were into killing algae. And so whenever a pond or a lake in Illinois would have an algae problem, they'd call the State Water Survey in, and my boss, Raman, and I would go down and take a look at it. And generally, we treated it with copper +2 ions. It turns out the copper +2 is very algacidal. It'll kill algae, a lot of different forms of algae. But unfortunately, the lakes and ponds in Illinois are less acidic and more alkaline. We could use a little acid rain to drop the pH of our lakes. So it turns out that there's too much hydroxide in our ponds and lakes. It's a little too basic. Well, it turns out that copper hydroxide has a very small KSP, and consequently, if you put copper +2 ions in a lake to kill the algae, a lot of it just precipitates to the bottom, again, because the KSP for copper hydroxide is too low. So our brilliant idea was to encapsulate the copper, to attach a couple ligands to it in order to keep it out of harm's way, meaning keep the hydroxides away from it. But we wanted to encapsulate the copper with a couple ligands, but we didn't want it to lose its algacidal effect. And since most of the lakes and ponds that we looked at were water supply impoundments, we couldn't use a ligand that was toxic, obviously, because it was somebody's water supply. Well, it turned out that citric acid was the one that we wanted. Now, citric acid is a molecule that's kind of U-shaped. It's got a carbonyl group on both ends of the molecule with lone pairs sticking out from the oxygen. Those lone pairs are the Lewis base part of this molecule that essentially will attach to the copper +2. As a matter of fact, since it bites on in 2 places, they call it a bidentate ligand. I like that, 2 sets of teeth. So the copper +2 would essentially end up with 2 of these This is a simple picture of it. I didn't draw the whole structure of citric acid. But it turns out that two citric acid molecules would latch on to the copper plus 2 and encapsulate it. Well, citric acid's non-toxic. It's good enough to work in a water supply. And we just had to check to make sure that the copper, once encapsulated, would still kill the algae. Sure enough, it did. All right, so it turned out a 2-to-1 mole-to-mole ratio of citric acid and copper plus 2, which usually we brought as copper sulfate, did the trick. And it would keep the copper in solution for days and days and days and kill the algae without all the copper precipitating to the bottom. All right, so there was kind of a use of some Lewis acid-base theory and some coordination complex theory in order to solve our little issue with copper precipitation. The rest of the story was, however, that Lake Loami, we went down there one year and we were very successful in killing the algae. We put the copper sulfate in, the citric acid, and the next day the algae turned kind of brown, and the next day it turned black, and then the fourth day, all the algae died and sucked all the oxygen out of the lake and killed all the fish and all the plants. And so it made the whole lake go completely anoxic. It didn't have any oxygen in it at all. And the reason they called us was because the algae smelled bad. Well, once it decayed like that, it smelled even worse, especially with all the dead fish. And so it took us all summer to resurrect that pond. It was a 10-acre pond. And so we had to replant arrowhead weeds around the edge. We had to re-aerate the lake. We brought in bubblers and hoses. It was a huge mess. So the next year, they called us again and said that they had an algae problem. And they were reluctant to call us considering what we had done to their lake the year before. But we went down, and sure enough, there's this Kelly green algae that's growing on their pond. And so we had kind of looked into the issue and thought, well, we need to supply some kind of an oxidizing agent. If this thing's so effective in killing the algae, we need something to help oxidize the algae so that it doesn't suck all the oxygen out of the lake. So we used potassium permanganate, KMnO4. Not much, about 1.5 pounds an acre is what we figured we needed to do the amount of algae that we were going to try to eat up. But potassium permanganate, when you put just a little crystal of it in water, it turns the water like dark purple, like Welch's grape juice purple. All right, well, we went down to the lake and we put the copper in the boat and the citric acid, and we put it in a burlap bag and we dragged it behind the boat, a little 10-acre pond, and we went around, and the next day the algae's turning brown, and the water treatment guys were looking at us like, well, this is kind of what you did last time. And Raman was like, don't worry, we got this. And so the next day the algae starting to turn black, and they're starting to panic, like, we're going to go through this all again. Well, that day we went out and dragged a big bag of potassium permanganate behind the boat, and it turned the lake completely purple. I mean, it was like Welch's grape juice purple. It looked so surreal. And I mentioned this before. I had a picture of it with the blue sky and the green grass and the purple lake. It just looked like a Salvador Dali painting, like there should be a clock melting over a tree somewhere or a cow flying through the air. But anyway, the next day, the potassium permanganate worked like a charm, and it ate up all the algae. We came back on the fourth day, and the water was absolutely crystal clear, and the fish were jumping and whistling, and so everybody was happy. But it turned out, yeah, if you're too effective in killing off the algae, you got to make sure that you provide something to help eat it up. So anyway, just a little anecdotal story about complex coordination chemistry. And I guess I'll see you Monday. We'll start our discussion of thermodynamics, the 3 laws of thermodynamics. We're going to go back and look at a couple things we talked about in Chem 130. We're going to look at Hess's law and calorimetry, those styrofoam cup calorimetry problems. And so we'll look at the delta H's of reactions again. But we're going to put a little bit more spin on it this time. We're also going to look at reaction spontaneity. What drives a reaction to go forward? And it turns out one of the big players in that is something called entropy, which is the randomness of a situation that's produced. So anyway, it gets a little bit more interesting than what we discussed back in Chem 130. We'll go a little bit deeper into the topic. And so keep an eye on your email, and I'll see you on Monday.